Thank you, Sihan, for the introductions. So today's talk will be split into 3 sections. Each section is a different many model serving solution in RayServe, although you can combine them in any way that you'd like for your use case. First, we'll dive into model composition. Generally, a big trend that we've seen recently is that more and more applications require multiple models rather than just a single model for inference. Some common examples are audio transcription, which requires multiple models to serve a single request, or computer vision, which also requires usually more than one type of image processing model, like classifiers or detectors, to serve that single request. But there's a lot of challenges that come with many model serving. The first one is efficient hardware usage, which really just means you have a certain amount of CPU compute and GPU compute. How do you use that as efficiently as possible, especially when you have a heterogeneous mix of models with different hardware resource requirements? Especially with the recent rise of LLMs, there's a huge GPU shortage right now, so every GPU counts. So it's especially important to be able to share your GPU resource compute between the models in your application. It's also important to be able to scale the models in your application independently of each other, especially if different models have different latencies or different traffic patterns. And then there's operational overhead. A lot of these things are important when you're doing development or when your application is running in production. Testing your application end-to-end should be simple. Observability and monitoring is really important in production to know how your application is doing or if something's going wrong. And being able to upgrade parts of your application independently of each other should also be flexible. But all of these become more complicated once you start adding more models to your application. Let's take a deeper look at the computer vision example we showed here. Suppose you take the raw image as input, pre-process it, and then run the pre-processed data through a classifier and a detector model, and then finally run some custom business logic to decide on the final output to return to the client. We'll be using this as a reference example for the next few slides. So how might you solve these challenges that we mentioned without using RayServe? The first thing that you might try is the monolith approach, which is essentially the shove all of your models into one box solution. You can take your models, put it into a container, scale the container up together as a monolith, and then that will be your service. But a big problem here is you aren't able to scale part of your application independently of the other parts, because everything is packaged together and glued together as one piece. For the same reason, you aren't able to make independent upgrades. If you upgrade one part of your application, all the other parts are forced to update as well, which makes the upgrade process both very risky and very costly. The next thing you might try is separating your models into individual microservices. You can have an API gateway for access control. There'll be communication between microservices, since each request requires multiple models for inference. And now you can scale up each microservice independently of each other. So like we said, there's independent scaling, and you can independently upgrade one microservice without affecting your other models. But it's exactly because everything is separated into its own system that you can't share resources between your models anymore. And you have to set up a lot of things like inter-service communication, maybe databases for each individual microservice. Monitoring and observability has to be set up individually for each microservice. Testing your application end-to-end is also much more complex now because you have to deploy multiple subsystems to test your application. So there's also a lot of drawbacks to this solution. This is why in RayServe, we built a feature that combines the advantages of both the microservices and the monolith approach, called model composition. So one application in RayServe consists of multiple models composed together. Each model can have its own hardware resource requirements. For example, some might run on a GPU, some might be CPU only, and some can even have a combination of both. You can also auto-scale the models in your application independently of each other. This means if one of the models in your application is the bottleneck, you can allocate more resources to that one model instead of having to scale everything up together. It also scales at a process level, which is even more flexible than scaling at a container level, which is what the microservices approach does. This means when you're scaling up your application, you don't have to necessarily add more nodes just to scale it up. You can add more copies of your model onto a single node until you've maximized the resource utilization on that node. And finally, something that using Ray uniquely gives us is the ability to use fractional resources. For example, if this single model uses half a GPU each. Having 3 copies of it means you can schedule all 3 copies on just 2 GPUs. And you can even use the remaining space for another model. Now let's see how we would go through this computer vision example using model composition. You take your image, pre-process it, send it to a certain classifier model and a detector model, and finally run your custom business logic. And this is your entire multi-model application. Notice how as we added components to the application one by one, we also showed what you would need to add on the right here to the Python file. The point here is you are able to define and link together your entire application using just a single Python file, and that's all you need to deploy your application to a RAID cluster. We can look at an example of resource allocation for this application. Classifiers might take 1 CPU and 1/3 of a GPU each. Pre-processing usually runs on CPU, so we can put those 2 deployments on a node with 4 CPUs and 1 GPU available. And then the detector and business logic probably also runs on CPU, so you can put those 2 on a second node with 2 CPUs available. So it's really easy to share resources between the models in your application. In a similar real-world use case, Samsara switched from using the microservices architecture that we mentioned to using RAID-serve model composition and managed to save 50% of their ML inference costs per year. Now let's revisit the challenges that we started with. Like we mentioned, it's really easy to share resources between models in your application, and you are able to independently scale models in your application. As for operational overhead, since everything is on the same cluster, testing your application end-to-end is easy, and it's very simple to set up monitoring observability for just your single RAID cluster. But if we limit ourselves to one single application, what we're missing here is independent upgrades. If you update one part of your application, it still requires updating all the other parts of your application as well, which is a perfect segue into the second part of our talk, which is multi-application. So like we mentioned, one application with model composition doesn't work for all use cases. Suppose you have an ML team working on computer vision models for autonomous driving. But maybe these models don't work well during the nighttime. So you have another team working on algorithms specialized for nighttime. And ideally, these would work. They would live on the same cluster so that the vehicle can just switch over to these specialized algorithms at nighttime. You might have another team working on algorithms for snowstorms or rainstorms. LiDARs and radars are also really important for gauging the exact distance between your car and other objects on the road. Ideally, all of these will live on the same cluster since they're all serving the same use case, but they're probably all living in different repositories and certainly managed by different teams. So if we combine all of them together into a single group using model composition, they would all share the same upgrade lifecycle. That means if one team wanted to make a change to their model in production, the models managed by other teams would be forced to update as well. So that makes the upgrade process risky, costly, and overall just very complicated. You might even need another team just to manage deployments across ML teams and making sure nothing goes wrong during deployment. This is why we added the multi-application feature, which builds on top of model composition. So your application can still have models composed together, but now you can have multiple applications living on your same RAID cluster. Each application is its own endpoint and has its own upgrade lifecycle, meaning you can easily add, delete, or update applications without worrying about affecting the other models on the cluster. At the same time, you still have the benefit of efficient and flexible resource allocation and sharing hardware resources between your applications. Let's just go through a really quick real-world use case of multi-application. AnyScale endpoints is the AnyScale hosted API endpoints for LLM inference and fine-tuning. And recently, the Llama family of models, as some of you might know, was released by Meta AI and has really great performance. So suppose it was just recently very released, maybe a few days ago, and we wanted to add this to AnyScale endpoints for our users to try out and fine-tune. So suppose you wanted to add the 7 billion parameter model to AnyScale endpoints. You would just have to add it to the config file, deploy it to the cluster, and this would load it onto your cluster, ready to serve users' traffic. You can also add more models, like the 3rd TB model, and then hypothetically, you could also delete that and replace it with the 7 DB model, all by using a serve config file and making changes to the entries. And notice how the entire time, the 7B model continues to serve traffic. regardless of what's happening to the other applications on your cluster. Again, let's revisit the challenges that we started with. Like we mentioned, a single application with model composition already, it gives you a lot of these benefits, like efficient resource allocation and independent scaling of the models. As well as testing your application end-to-end is very easy. Observability and monitoring only has to be set up once for the entire cluster. But the one thing that was missing was independent upgrades. With multi-application, you can group the models on your cluster into groups that make sense to you. For example, if they're living in different repositories already, or they're managed by different teams, or any other requirements that you have, you can form those groups and then update those groups independently of each other. Now I'll hand it off to Sihan for the rest of the talk. Yeah.
Thank you for Cindy deep diving the model composition and multi-application use cases. In previous scenario, we typically loading all the models into the server clusters at once for serving. But as we see the emergence of the LLM use cases, we see serving a large number of models require more resources than what your provider can provide. The cluster can provide. So to support this scenario, we introduced a new reserve API, which is called multiplex, to support this use case. Before going to the API, I want to go for simple examples. Let's imagine we want to build a LLM inference platform service, such as like Unscale Endpoint or Firefox AI. And we want to support different open source model, for example, like different number of parameters of the Llama models. And more importantly, we want to supporting different customer models to supporting their own business use case. So this is going to be the two challenges for supporting this use case. One is the limited hardware resources. So you're typically not able to loading all this model into your cluster at once. One is like it's very expensive, especially for GPU hardware. Secondly, for inactive models, it's not very efficient. You load these models into your memory without being used. Second challenge is the high inference latency. If you're loading the models all the times, your online inference service will suffer the cold startup time all the time. So let's see how it looks like without multiplexing. So normally, we put in all our model into the S3. And user will just specify your model ID and sending the HTTP request to your clusters. And the cluster proxy receiving this request. Right now, there's no, for these examples, we're using the two replicas in this cluster. Proxy will randomly pick up replicas to serve this request. Let's say we go for replica 1, and we're loading the model from S3, and load the models, and do the inference, and get response back to the client. If client keeps sending the model 1, given proxy doesn't even know what the model ID is located, what the model is located in which replicas. So proxy potentially will choose replica 2 to serving your request, which means you have to loading the model 1 again into the different replicas from S3 into your clusters to serve this request. That's the same for the model 2 and the model 3. Think about if you have a large number of models, you have lots of models on S3, you end up have to swap in your models given your hardware resources, and the code inference, code start time will be very high for your online inference. Let's see how the multiplexing resolve these issues. It's the same. Let's say client also set the model 1 into the HTTP request, and sending the proxy, and this is the same with the previous one. We're loading the model into the replica 1 from S3 and do the inference, get results back. If user send the model 1 again, with multiplexing API, proxy will know model 1 is located inside the replica 1. It will smartly routing the traffic to the replica 1 to do the inference, instead of choosing different replicas. So in this case, you are able to do the model 2 and model 3 with the same. So with saving the more memory, you're potentially saving more resource for loading all the models from your many model use cases. This is how the multiplexing works to help you to boosting your performance. We also did a benchmarking with SageMaker multimodal endpoint. So SageMaker multimodal endpoint is a similar technology for serving these use cases. We're using the 100 JustNet50 models with 4 M5 large instances. And we're using the HTTP client to choose the different image categories, sending the image to the clusters. And based on the different categories, we're loading the models into our replicas and our worker in the SageMaker and to do the inference. And this is the result that we get from the benchmarking. The green one is the baseline. Baseline is the no multiplexing, which I show you at the first. It's going to end up like very bad throughput because you have to swapping all the models all the time. The blue one is the SageMaker one, and the orange one is the reserve multiplexing. As you can see, reserve multiplexing from our benchmarking is around like 30% better throughput than the SageMaker. The main reason for the better throughput is the model cache hit rate. So the model cache hit rate means whenever proxy routing the traffic to specific replicas, if replica already hold this model into the memory, we take as a model cache hit. Otherwise, we take as model cache miss. So as you can see, reserve multiplexing is better than the SageMaker one from our benchmarking. With better cache hit rate, reserve can avoid model loading times as much as possible than other solutions, so that we can maintain better latency and a very good throughput in this case. Now, let's look at how the multiplexing use case into the Anyscale endpoints. As I gave you the examples, Anyscale endpoint is the platform to supporting different LLM use cases. We also have these challenges. As I mentioned before, we have very limited resources. We want to maintain very good latency in this case. We're using LoRa techniques to reduce models. With LoRa, we are able to make the customer share the models with one big base model and loading into memory. So customer doesn't need to so each customer doesn't need to load all the models into memory. So let's see how it looks like, how we combine this LoRa and the multiplexing together into the Anyscale endpoints. Whenever we start the replicas, and we will load the base model first into a GPU memory. And whenever we receive the request, we are loading the model from our S3 and CPU memory and GPU memory to do the inference. With the multiplexing API, we are able to routing the traffic for specific model to the specific replicas. In this case, we are able to maintain very good cache hit rate and to avoid model swapping all the times, so that we are able to support many more models with our limited hardware resources. Now, I'm going to hand off to John to talk about the Clary use case.
Thanks, Xian. So first of all, what does Clary do? Clary provides a platform for revenue operations. You can think of Clary products as a superset of CRM application. One of the products we have is forecasting what the sales is going to look like at the end of the quarter. We use AI model. We build this AI model per customer using per customer data set. So what are the problems that we have? Since we build the model per customer, we could have potentially thousands of models. We have multiple versions of the same model because we continue to improve the model performance. And each model could have its own deployment cycle. On the inferencing side, we make online inferencing because we want to use the latest sales activity data to make accurate prediction. On the traffic side, we experience uneven traffic patterns depending on the time of day, week, or month. Another interesting aspect is that these models are invoked sparsely, which means we don't have to load all the models all at the same time, but there will be a set of models that will be used at a given time. But we cannot predict which models are going to be used at a given time. So before I talk about how Ray helped us with this scaling challenge, I'm sharing cloud-native-based solution. So we take model code, build a custom train container, and put it through Airflow pipelines, and have cloud-native train service to train the models, and also use cloud-native service endpoint to serve those models. It worked initially, and actually works up to a few hundred models. But once we pass that number, when the number of models gets larger, we started seeing a scaling problem. So with Ray, we were able to cut down the number of components. And more importantly, we were able to see a significant boost in the performance in both the training time and also serving latency. Sharing our POC test numbers, you can see that training time was reduced by about 80%, and also cold start latency was reduced by more than 80%. The cold start latency is important to us because these models are invoked sparsely, and there will be a lot of model swapping happening. Some additional benefits that we got from Ray Serve is the memory efficiency. As Xian said, the multiplexing does a really good job in managing the model loading into replicas. We don't have to load the model in every replica, but to only one replica. Also, we get the auto-scaling out of the box. These native solutions or auto solutions could provide maybe a better performance by tuning or adding additional engineering resources to it. But Ray just worked out of the box. Also, we could use a single service to serve all these models, while each of the model is having its own life cycle. One of the cool thing about Ray Serve is that it's very easy to integrate with our own code. All we have to do is throw a few Python decorators to existing fast API implementation. With that, I'll hand it back to Shihan.
Thanks, John. So I'm going to do a recap for this talk. So Ray Serve support different solutions to support different mining model use cases. We talked about the model compositions, how you boost your hardware resource with hybrid clusters, how to independent scaling your each component. We also talked about the multi-applications, how to simplify your end-to-end model ML life cycles, how to manage different use cases with single clusters. And also we talked about the serving large number of models with Ray Serve multiplexing. It can get the 2x performance boost from the baseline. Hopefully, I can get all these features inside the Ray Serve 2.7. Check out to use it. Thank you for coming. Any questions? Yeah, I think there's two questions. One is the model deployment. So in the current multiplexing, model deployment can be deployed on the fly. So users specify the model ID, and the users specify the model loading functions. So with the model ID and model loading functions, Ray Serve will run this function to loading the model from your disk or S3. And to know which model is located inside the replicas, so we are broadcasting the information to the proxy. And after loading is done, and proxy will know which replicas having these models, and we will serving the traffic following this pattern.
So there's only one cluster for all models?
There's only one
cluster?
Yes, that's true.
Oh, okay.
Yep.
Thank you. So with the multi-application scenario, is there a limit on how many applications we can have per cluster, or any recommendations on how many applications we should have?
The question is, do we have any limit how many applications that we have to support in one cluster, right? So we don't have specific. We are doing some benchmarking with thousands of applications. It potentially having very little reconciling overloop, reconciling latency in the controller, but it can be supported. But most likely, you also need to. We're also testing some thousand nodes, so it's also working fine. So hopefully, it's answer your question. But it also depends on your per clusters use case. Yeah. Any more questions? Yeah.
So the multiplexing is in beta, right?
Yes, this is in beta. That's true. Oh, okay, that's a good question. So, so multiplexing, we are trying to gather more use cases to be in production. So we potentially have some further improvements to make it generally available. For example, like more memory protections for your multiplexing. But right now it's under the beta, so yeah. Any more questions? Cool, thank you. Thank you very much.